So emitter bias, let me start with, okay. So you can just write down for the circuit shown below, determine the following: IB, IC, VCE for beta equal to 50 and beta equal to 100. So find VC, VE, VB and VBC. Okay. Solution. Okay. Now the circuit is given, and you have been given with the different component values, right? All resistance values have been given, and you have been also given with the capacitor connections, right? So this is your AC input VI, and this is where you will observe your AC output. Okay, capacitors, will they affect biasing operation? Biasing is purely DC operation. Okay, for DC, capacitors offer infinite reactance. Okay, and therefore capacitors can be treated as open circuit elements for DC analysis. This is very, very important. So capacitors can be treated as open circuit elements, okay, for DC analysis. So that's the reason what I will do. I will erase the capacitors. Okay. So entire AC operation can be isolated. Okay. Okay. So for I mean, normally what they will do in the exams, so these capacitors will be given just to confuse you guys. Okay, but remember, biasing is DC operation, and for DC, capacitors offer infinite reactance. Infinite reactance in the sense current flow through the capacitor element going to be 0 for DC voltages, right? Hence, you can remove those capacitors. So your circuit becomes a purely DC oriented circuit. Okay. Fine. Now you can start solving the problem. Okay. Since you need to find the Q point for beta equal to 50 as well as beta is equal to 100, what we can do is we can take for beta is equal to 50 as our current gain, and for beta is equal to 50, let's calculate IB, IC and VCE. Okay. So let's calculate IB. So IB for emitter bias circuit is VCC minus VBE divided by RB plus 1 plus beta times RE, or IB is equal to VCC is 20 minus VBE. It's a silicon transistor, so it's 0.7. RB 430 kilo ohm, that is 430 into 10 to the power 3, plus 1 plus beta, that's 1 plus 50 into RE. What's the value of RE? Is 1 kilo ohm. Okay. So IB. Okay. So let me take this IB as say IB1. Okay. Because I'm taking beta as beta 1. So IB1, let me write. Okay. IB1. And IB1 is equal to how much you'll get? Did anyone calculate? You get roughly about 40 microamperes. Can anyone confirm? 40.1 microamperes. Okay, is it correct? Can anyone confirm? And then you can get the value of IC1. So IC1 going to be beta 1 times IB1. Okay, so beta is 50 into 40.1 microamperes. So 50 into 40 is about 2000 micro. So that is close to 2 milli, I guess. So IC1, let me use the calculator. Okay. How much you'll get? IC1, 2.01 milliamperes. milliamperes. Okay. So that's your IC1. Okay, let me round off even IV1 value. IV1 value. Fine. Okay. It's fine. IC1, you could get it. Yeah.
Yes, sir.
Yeah, fine. So once that is done, probably you can go for the other calculation. Okay, VCE1. Okay, can anyone tell me what's the value of VCE1? VCE1. So VCE1 is what? For emitter bias circuit, it is VCC minus IC into RC plus RE. RC plus RE. Just inserting the pages. All right. Yeah. So VCE1 I was talking about, right? So VCE1 is VCC minus IC1 into RC plus RE, or VCE1 is equal to VCC is 20 minus IC1. IC1 is 2.01 milli and RC is 2, RE is 1. The unit is kilo ohm, so 10 to the power 3. Let me keep it outside the bracket. So milli and kilo gets cancelled. So VCE1 going to be 13.97. Is it correct?
Yes. Yes, sir.
13.97 volts. Okay. So that is your VCE1. Okay. So let's calculate VC. Okay. So what is VC? VC is collector to ground voltage. Okay. This is VC. VC. Collector to ground voltage. So collector to ground voltage is equal to collector to emitter voltage. Okay, this is plus, this is minus, and then emitter to ground voltage. This is plus, minus, right? Collector to ground voltage is equal to collector to emitter plus emitter to ground. Okay, so we can write VC is equal to VCE plus VE. Okay, where VE is equal to voltage drop across emitter resistor, that is IE into RE. Okay, or what is IE? IE can be written as 1 plus beta times IB, right? IE can be written as 1 plus beta times IB into emitter resistance RE. Okay, so what you can do, you can directly find out VE, right? So VE is equal to 1 plus 50 into IB. IB you have already found, right? That's 40.1 microamperes. 40.1 into 10 to the power minus 6 into RE. RE is 1 into 10 to the power 3. So how much will you get VE value as? How much you'll get? Around 2 volts?
2.04.
Okay, 0.4 is it? Yeah, 2.04 volts. Okay, so that's your VE. So having known VE, you will be able to find VC. Okay, so you can substitute VE in equation 1. So you would get VC. Okay, let me put it inside a box. Okay, so VC is VCE. Okay, so VCE you have already found for beta equal to 50. that is 13.97 plus 2.04, or VC is equal to 15 point change, right? 15.98 volts. So that's your VC. Okay. So you have found VE, you have found VC. Now you need to find VB. Okay, what is VB? Let's go back to the circuit diagram. By definition, VB is defined as base to ground voltage. Okay, so here is our VB, base to ground voltage. So if you look at base to ground voltage from the input side, you would see that base to ground voltage is equal to summation of base to emitter voltage plus emitter to ground voltage. So base is at higher potential, emitter is at lower potential. Okay, but when you find out VE, okay, so emitter will be at higher potential and ground will be at lower potential. So VB, base to ground voltage, is equal to base to emitter plus emitter to ground. So it is VB plus VE, or VB is equal to, VB is 0.7 for silicon transistor and VE is 2.04, you have told me. So VB is equal to 2.74. So that's your VB. Okay, so let me just mark. We have found VC, we have found VE, we have found VB, and finally we need to find out VBC. So VBC is equal to VB minus VC, or VBC is equal to VB 2.74 minus VC. How much did we get? VC as 15.98. 15.98. So that gives VBC is equal to minus 13.24. Okay, fine. So that's your VBC. Okay. Now in the second part, okay, let us recalculate IC, VCE, IB for beta is equal to 100. So let's recalculate IC, VCE, IB for beta is equal to 100. Okay. All right. So we have IB2 expression. Okay, IB2 expression for beta 2. Okay, that is VCC minus VB RB plus 1 plus beta 2 times RE. Okay, so IB2 is equal to, the numerator will not change, 20 minus 0.7 divided by, the resistor values will not change, 413 to 10 to the power 3 plus the beta value. Okay, over here the beta value is going to change, right? So it is 1 plus 100 into 1 kilo. Okay, so IB2 you will get it as okay, when beta increases, right? So this is the observation basically. So when beta increases, your base current should reduce. So base current becomes, just check, 36.3. Did anyone get it?
Yes, sir.
All right. Yeah, as expected, with the increment in beta, base current should reduce, and that gives the bias stabilization. So once you get IB2, you can find out IC2 is beta 2 times IB2. Okay, so that's 100 times IB2. Okay, so IC2 is 3.63 milli. You should get 3.63 milliamperes. Okay, so once IC2 is found, yeah, once IC2 is found, you can find VCE2, that is VCC minus IC2 into RC plus RE, our output KVL equation, or VCE2 is equal to 20 minus IC 3.63 into 10 to the power minus 3 into RC plus RE, that is 1 kilo ohm, and sorry, this is 2 kilo ohm, and this is 1 kilo ohm. So that is 3 kilo ohm. So this gets cancelled. So you will get VCA2 is equal to 9.11. Okay, 9.1. Fine. So once you identify the Q point, so what we will do, we will just write Q1 as IC1 comma VC1 is equal to, okay, so IC1 is 2.01 milliamperes, comma, VC1 was 13.97 volts, okay, and Q2, okay, the coordinates are IC2 comma VC2, and that's equal to 3.63 comma 9.1. Okay, so that's your Q point, okay, for the two values of beta. Okay, so this should help you in plotting the load line graph, right? So let's plot the load line graph now. So what I'll do, I'll just construct the load line graph. Okay, so this will be our IC saturation and this will be our VC saturation. This is your IC saturation and this is going to be your VCE saturation. Okay, so let us also join these 2 points. Okay, IC saturation is VCC divided by RC plus RE 20 divided by 3 kilo ohm. So IC saturation is equal to 6.67 milliamperes. Okay, and VCE saturation is equal to VCC. Okay, that's 20 volts. Okay, so this is your 20 volt, and this is your 6.67 milli. Okay, you can say that current is in millis of amperes and voltage is projected in volts. Okay. Okay, say this is 10 volt, say this is 5 volts, this is origin 0, say this is 15 volts. Okay, so this is about 2, this is 4, this is about 6. Okay, approximately, you don't have to do what you say a very accurate load line. Okay, approximate load line you can do it. Okay, then just place the Q point. Okay, the first Q point is at 2 milliamperes and 13.7. So somewhere here, somewhere here. So So that's our first Q point. I don't have to write the location, right? Because I've already defined the coordinates of point Q1. Similarly, I have to place Q2 now, okay, which is at 3.63 and 9. So 3.63 is somewhere here, okay, rough, and 9. Okay, 9 will be somewhere here, correct? And this is about 13. Okay, and this is about 2. This is your Q point. Okay, as you can observe carefully that in case of emitter bias circuit, due to the variation in beta, okay, so this is for beta 1 and this is for beta 2. Okay, the Q point has moved, okay, not by a significant margin, but on a lighter note, you can say that slightly it is being moved from the desired location. Okay, so not bad as compared to fixed bias, but not good as compared to voltage divider bias, right? In one of the class, we did a voltage divider bias problem. You can go back to that problem and you can compare the Q point drift. Okay, so that completes the emitter bias problem. All right. So now let us look at, let's say, collector to base bias problem, and let's see how the Q point variation takes place in collector to base bias problem. Okay, all right, fine. So next you write down collector to base bias problem. Okay, you can write for the circuit shown below. For the circuit shown below, determine the following. Okay, write down IB, determine the following, that is IB, IC and VCE. IB, IC and VCE for beta variation from, for beta variation from 90 to 180. Okay. 90 to 180. What happens when beta is fixed at 90 and what happens when beta is changed to 180? Okay, so doubling effect you're supposed to assess. All right, so this is the given circuit. Okay, so you can mark the currents. You know that current through the emitter terminal is IC. This is IE, and through the base is IB. So current through RC going to be IC plus IE. Okay, IC plus IE, and it is a silicon transistor. Fine. So solution. So you need to find out what the base current first. Okay, so I want you to roll back to collector to base bias circuit. So in collector to base bias circuit, okay, just let me know what do you get the base current expression. What do you get the base current expression as? IB is equal to VCC minus VCE CC minus VBE, sorry, divided by RB plus 1 plus beta times RC plus RE. Is it correct? Can anyone confirm?
Yes, sir.
Right. Fine. So IB is equal to VCC 10 volts minus VBE 0.7 for silicon transistor, RB 250 kilo. I'll just write K. Okay, K means 10 to the power 3 plus 1 plus beta. So that is 1 plus 90, right? 1 plus 90 into RC plus RE, 4.7 plus 1.2 kilo. Okay. Okay, I will written. Right. So IB is equal to, okay, just let me know, 11.82.
818 microns.
Yeah, 818. Good, good. 11.82 microamperes. Okay. So let me take that as IB1. Okay, that's because we have calculated IB1 for beta 1. Okay. And then you can find out IC1 quickly. So that is beta 1 into IB1. 90 times IB1, 11.82 micro. So IC1 going to be 1.06.
1.06.
Yeah, 1.06 milliamperes. Once IC1 is calculated, you can find VCE1. Okay, VCE1 is VCC minus IC times RC plus RE. So it is VCE is equal to 10 minus 1.06 milli into 4.7 plus 1.2, that is 5.9 kilo. Milli and kilo gets cancelled. So you will be left with VCE is equal to
3.741 volt.
right 3.74 volts. So that's your VCE1. Okay. And now what you do is take beta is equal to 180 and say that is beta 2. Okay, so for this fresh beta value, you need to recalculate the coordinates of the Q point. Okay, starting with IB2. Okay, I think I can directly write it. It's okay. I'll write once again. VCC minus VBE divided by RB plus 1 plus beta times RC plus RE. Okay, so that gives IB2 is equal to, okay, 10 minus 0.7 RB. RB is 250 plus 1 plus this. I will take beta 2. Okay, that is 1 plus 180 into RC plus RE, that is 5.9 kilo. Correct? 4 plus 5, yeah, 5.9 kilo ohms. So that will give you IB2 value. Okay, how much you'll get IB2 as?
7.05 microamps.
Okay. 7.05, right? So it is 7.05 microamperes. Okay, that's your IB2. Once IB2 is found, you can find out IC2, beta 2 times IB2. That is 180 times 7.05 micro. So that becomes 1.27 milli.
Yes, sir.
1.27 milliamperes. Okay. And finally, VCE2. VCC minus IC2 times RC plus RE. Okay, so VCE2 minus, okay, is equal to 10 minus 1.27 milli into 5.9 kilo. Milli and kilo gets cancelled. 2.5. Is it correct? 2.5 volts.
Yes, sir.
Yeah, right. Fine. So what we have done, we have calculated the coordinates of the Q point for two different values of beta. Okay, so let us place them now. So first let me write Q1. Let me define Q1 as IC1, VCE1. Similarly, let me define Q2, that is IC2, VCE2. Okay, and that is equal to IC1. How much did you get IC1 as? IC1 is 1.06 milliampere, VCE1 3.14. Okay, and then IC2, okay, 1.27 milli, VCE2 2.5. Okay, 2.5. I don't know whether you recall the emitter bias answers. In emitter bias, the difference in Q point was slightly bigger as compared to the Q point variation in collector to base bias. Okay, but if you look at the voltage divider bias, the difference in Q point, okay, against beta variation is negligibly small. Okay, fine. That will be our final conclusion. Nevertheless, let's draw the load line first. Okay. Your IC. And that's your VCE. Okay. IC, VCE. Okay. This is your IC saturation. This is your VCE saturation. Okay. So VCE saturation, that is 10 volts. And this is IC saturation. Okay. That is VCC divided by RC plus RE. Okay. So 10 divided by 5.9. That's 1.7 milli. Is it correct? 1.7 milliamperes. The IC saturation. Okay. Okay, fine. Now let's place the Q point. This is 10 volts. So this is 0 volts. Okay, the center going to be 5 volts. Okay. This is 2.5 and this is 7.5. So this is your 1.7 milli. Okay. So let's say this is your 1 milli and somewhere here 2 milli point lies. Okay. So if this is 1 milli, say this is 0.5 milli, and let's say the half going to be 1.5 milli, which will help you in plotting the load line. Okay, what's the first coordinate? 1 milliampere and 3.14. So somewhere here it is. Q1 for beta 1. And then you have 1.27 and 2.5. So 1.27 somewhere here itself. Okay. This is Q2. So drift is very small. Drift is very small. So that's what you can conclude. Okay. So conclusion from now, what we have done is we have solved 4 problems for 4 biasing network. So by comparing the Q point drift against beta variation, you can say that voltage divider bias will have least or minimal drift in Q point. Okay. On the other hand, fixed bias has maximum drift in Q point, and that's the reason this is the best circuit when it comes to stability. Okay, and this is the worst circuit when it comes to stability. And then you have the 2 intermediate circuits, collector to base bias, okay, and then emitter bias. Okay, so Q point drift is small, you can say, and here you can Q point drift is moderate. Okay, something like that you can conclude. Okay, this is called as quantitative assessment with the help of physical resistance values, okay, and the circuit parameter variation. You could gauge the performance of the 4 biasing circuits. So VDB, voltage divider bias, is best, fixed bias is worst, so collector to base bias is, you can say, very good, and this you can say good. Okay, that's how we measure the goodness of a biasing network in terms of stability. And stability is measured in terms of beta variations, in terms of collector to leakage current variation, or in terms of base emitter voltage variations. Okay, but in our problems, we have analyzed the biasing stability in terms of beta variation, and beta can vary due to the transistor change or due to the variation in the temperature. All right, so that concludes today's class. Okay, in the next class, let me take up the design problems. All right, thank you so much.